Through rain and snow, hurricane, typhoon, and monsoon, flash flood and bomb cyclone, for 10 years, the joint NASA-JAXA Global Precipitation Measurement Mission has measured a lot of water. GPM's core Observatory satellite launched from Tanegashima Space Center in Japan in early 2014, becoming the first satellite to be able to see through the clouds and measure liquid and frozen precipitation from the equator to polar regions using a radar.
GPM will give us a much better picture of rain and snow falling across our planet. Knowing when, where, and how much it rains or snows will improve our understanding of Earth's weather and climate cycles.
Now, in its 10th year of operation, we look at 10 events brought to light by this groundbreaking mission. In its first year, the GPM Core Observatory satellite caught the heavy rains of the Indian monsoon. The monsoon is a seasonal wind and rain pattern that can account for up to 60% of the region's yearly rainfall. GPM allowed us to see precipitating systems like monsoons as a whole over both land and ocean. These satellite data allow researchers to study the variability of the monsoon, as well as how they impact agriculture, flooding, and landslides in the region. In 2015, Tropical Cyclone Kilo slowly meandered across the Pacific Ocean for 21 days. Because of its long lifespan, Kilo created a kind of open ocean laboratory for the mission to study the development of the tropical cyclone in a way only possible with a global satellite. Kilo was so long-running that GPM caught it 6 times, and as both a hurricane and a typhoon after it crossed the international dateline. In September 2016, Matthew became the first Category 5 hurricane in almost 10 years. It strengthened from a Category 1 to a 5 in less than 24 hours, leaving a wake of destruction in its path. As Matthew traveled through the Caribbean, data from GPM and a suite of other satellites allowed researchers to create a multidimensional picture of the hurricane in order to study the complex atmospheric interactions. Less than a year later, Hurricane Harvey became a Category 4 as it made landfall in Texas. Soon after, Harvey quickly lost speed and slowly inched up the coast, resulting in a record-breaking amount of rainfall, topping 4 feet in some areas. GPM was able to track Harvey and the ensuing flooding because of its product called eMERGE, the Integrated Multi-Satellite Retrievals for GPM. eMERGE combines information from whatever group of satellites is operating in Earth orbit at a given time and estimates precipitation over the entire globe. This way, no matter where the GPM core satellite is, NASA can track the impact of precipitation systems and provide half-hourly data to local and regional agencies. It isn't just for rain. In fact, GPM became the first NASA satellite to measure the full range of light and heavy rain and falling snow. In January 2018, GPM observed a rapidly intensifying, or bomb, cyclone, which is marked by an extreme drop in central pressure of the system. The radiometer and radar instruments on the GPM Core Observatory allow it to see inside the storm and observe the frozen precipitation high atop the clouds. It can measure, layer by layer, the size and distribution of snow particles, which can help improve the numerical weather forecasts of snowfall. A Category 5, Hurricane Dorian became the most intense tropical cyclone to hit the Bahamas. As it churned northward toward Florida, GPM observed an important event in hurricane evolution, an eyewall replacement cycle. Here, the initial, compact, more intense eyewall is replaced by a broader eyewall, robbing the inner eyewall of moisture and angular momentum, resulting in a weakened storm. Predicting eyewall replacement cycles is difficult for forecast models, and detailed data from GPM can improve the accuracy of those forecasts in time. Hurricane Laura was the strongest hurricane to make landfall in Louisiana in over 50 years. To study it closely, the GPM core observatory's instruments were able to quantify and compare the distribution of precipitation drop sizes. It sounds like too fine a detail, but drop size distribution can tell researchers how droplets are colliding and coalescing within the storm before, during, and after landfall. This close look at the microphysical environment can help improve numerical weather forecasts and complex climate models. GPM can show more than single storms. It can cover precipitation over years, showing us longer-term phenomena like El Niño and La Niña. These large-scale climate patterns in the Pacific Ocean can affect weather worldwide.
We need the long-term record in order to know how what's happening now is comparing to the averages and previous extremes. Basically, what's the climate? These data are really important for telling us whether we should expect variations such as we're seeing or whether perhaps they're new extremes.
A big part of the GPM story is seeing the extremes, both near and far. Early 2022 brought Australia's worst recorded flooding disasters. With eMITS, GPM was able to track and measure the heavy and persistent rainfall from a series of storms that battered the northwest and east of Australia. Providing half-hourly rainfall estimates for agencies and resource managers around the globe has revolutionized the tools to help with floods, droughts, agriculture, and disease outbreaks. For 5 weeks, GPM tracked Tropical Cyclone Freddy, the longest-lived tropical cyclone on record ever. Freddy began over the waters between Indonesia and Australia and slowly progressed toward eastern Africa, causing flooding and destruction in Madagascar and Mozambique. Over the course of the storm's history, eMITS revealed a variety of rainfall features and trends that relate closely to the variations in Freddy's intensity. For instance, being able to analyze the surface rainfall intensity and where it occurs relative to the storm's center is valuable for studying the evolution of tropical cyclones. When it comes to climate, what is normal? That's kind of a big question. But providing the best picture of what's actually happening is climatology. And GPM has made big strides in defining the annual cycle of precipitation climatology. GPM isn't alone. It stands on the shoulders of its predecessor, TRMM, the Tropical Rainfall Measuring Mission. With TRMM's launch in 1997, developing a fine-scale global precipitation record began in earnest. And while TRMM lasted until 2015, it built the foundation of that long record. Today, GPM not only has added another decade of data, but reanalyzed TRMM's data with modern algorithms. This long and growing record gives climate researchers a good estimate of what their models and results should reveal in the current era. As we continue to see climate change impact our seasons, our regions and towns, and our livelihoods, we want to know how rain and snowfall will change, where extreme weather will occur, and how often. The data from GPM continues to help researchers build on a long record of past precipitation in order to set the stage for understanding the future.